All right, y'all. Welcome to another rousing edition of statistics and in this case, SPSS workshop. Typically, we're doing an Excel workshop, but this time we're going to be doing SPSS. And so today we are going to be looking at t-tests. And specifically, the one sample test, the paired sample test, and the independent sample test. All right, so these are our three main t-tests. And so for those of you who are unfamiliar with SPSS, which is the statistical package for the social sciences, I believe is the acronym here. That's my web browser, but this is SPSS, and SPSS is similar to Excel. It is a data package specifically for data analysis, quantitative data analysis. And so as you can see here, we have our package and our data, right? And so there's three basic components of SPSS. You have your data set here. Within that, you have your variable view and you have your data view. So this shows you your raw data for each case, case 1, case 2, case 3, so on and so forth. Variable view gives you a description of each of your variables. Then you have what is called syntax, and so this is syntax, and syntax is what syntax does is allows you to code. So it's essentially a coding mechanism, and what you can do is you can manipulate your data and run data analysis essentially using code or computer programming code, right? And so it's a more basic form of coding. And some packages are more difficult than others to learn. SPSS can be fairly difficult to learn. It's got a lot of commands, but the nice thing about SPSS, it has a point and click function, so you can actually point and click your way through and then paste your syntax or your code into the syntax box, and I'll show you what I mean. So today, again, we're going, and then the third piece is the output, which you will see, you'll see in a minute. And so today we're going to be going over one sample, paired sample, and independent samples t-test, and we'll go through each of these steps. I'm not going to go over all steps for all tests. That would just take too long, but I will at the bare minimum do step 2, 3, and 4 for each of the tests. All right. And so let's go over our data real quick, and then we can jump into some analysis. And so what I have here is data. Okay, that's me having a meeting. What I have here is data from Rate My Professors, from the website Rate My Professors. And so what my class did here is we went online. I randomly selected faculty from my institution. We went online and gathered their schools, so what school they were in: business, STEM, interdisciplinary arts and sciences, education, nursing, and health studies. So this is the qualitative, or in SPSS, what they call string variable. This is the numeric representation of that variable. We went up to their website, identified what their rank was: assistant professor, full-time lecturer, so on and so forth. Again, this is the string variable. Q2_n is the numeric value. We originally did this in Excel and SPSS. You don't need both of these. SPSS has that information within the numeric value. Then we went to their website, their faculty page, and checked whether or not we could identify their race, or at least perceive what their race was. Again, the numeric value for the string variable. And then if there were any others. And so we have actually one case where somebody didn't have a bio. Other than that, everybody had some information. Q61 is the rating on Rate My Professor, and so let's go to the variable view here. Q61 is overall quality. Q62 is, and these are on 5-point scales, level of difficulty. So the more difficult, the higher. Percent of students who would take again, and that's the percentage of ratings who said that. And the total number of people who would take the class again, whether or not Rate My Professor has this weird thing called the chili pepper. So if students find you attractive as a faculty member, as a professor, then they'll give you a chili pepper, which seems a little strange to me, but that's what happens, and it's data, so we grabbed it. And then we also looked on the faculty salary page for the University of Washington. Since we are public employees, we can find that out from the state website, which we did. And then, so the website's only up to date. It's 2 years old. So it's currently 2017, and so we have 2015, and then I calculated the standard raise at 2%, the standard living increase for 2017, 2% times 2 years. And that's how we did this. So those are all of our data, right? And so what t-tests do, let's just kind of give a general idea here. What t-tests do is they calculate the mean difference of some interval ratio variable across two different groups on some other variable, right? So for t-tests, we have an IV, and I'll do that like this, IV. And what I'm doing here in just to note in the syntax is I'm taking notes. And so if I put the asterisk here, it allows me to keep the note. So and it won't run it as a command in the file. So we have independent variables here, which equal one nominal variable with 2 groups. And then we have one DV, or dependent variable, one interval ratio type of variable. SPSS calls interval ratio variables string variables. All right, so keep those in mind. So let's go through this process. So let's start with the one sample test. So let's start with step 2, state our assumptions. We don't necessarily need to do that. They're assumed. We just need to know they're there and that we are not violating those assumptions. So step 2 here, state a research question. So let's start with that. So we're going to start with a one sample case. And what I'm going to do here to break up my notes from my commands is I'm going to create a line here. One sample t test. Okay, so state a research question. So let's go check out our data. So I might be interested in something to the effect of, does University of Washington faculty do in 2015, so here's their salary in 2015, how do they compare to faculty, let's say at Michigan State University where I did my graduate degree? So let's go check that out. And so what I did beforehand is I actually looked up Michigan State faculty salary, and I found, and I calculated it across the board, and I found that it's roughly, let's say 106,000. We can round up a little bit. So what we're doing here with a one sample test is we're comparing whether or not Michigan State faculty make more money than University of Washington faculty, more or less money. And we should be specific, University of Washington Bothell faculty. So my research question might be something to the effect of, does Michigan State faculty, wait, I'm going to reframe this. Is there a difference in salary for 2015 between MSU faculty and UW Bothell? faculty, right? And so a sub-piece is directionality. Because I stated a difference, I didn't state direction, right? I didn't say Michigan State faculty made more or less. I just stated a difference. So a difference equals a two-tailed test. So it's important to know that no directionality. If you're stating a direction, your T statistic or your T critical region is actually going to be different than if you don't state a direction, and you'll see what I mean. So that's our first step here. So we stated a research question. Step 3, actually I can go copy this. Step 3, we want to state the null in research hypothesis. So I would say null equals, or the null is, MSU is not different than UW. My research hypothesis would say that MSU is different than UW, right, on salary. So those are our two research hypotheses. Then what we need to do is calculate the test statistic, and this is where SPSS does the work for us. So I'm actually going to jump into analyses and start conducting some analysis here. So for the one sample test, what we're going to want to do is, first I actually want to do statistics. So I want to do some descriptive statistics here, which gives us some ideas about our data, right, and the variables we're going to be using. So right now what I'm going to do is I'm going to go to Analyze, Descriptive Statistics, and I'm going to go to Descriptives. And I use descriptives when I'm looking for a mean or an interval ratio type of variable. And the variable of interest for this analysis is faculty salary 2015. That's our dependent variable. So I'll throw that in our variables. We want the mean, standard deviation, min, max. You could do range too if you'd like. It's completely up to you as the researcher. Okay? So I did that by clicking on options. And then actually what I'm going to do is I'm going to click paste. And the reason I'm going to do that is it's going to actually paste the syntax into, or the command into my syntax box here. And so what I want to do is I want to grab this data and I want to calculate my test statistic. So I'm going to put it under that because that's the first piece. Don't necessarily need this, so to simplify I'm going to take that away. And so we have our descriptives here of Q10, and the statistics we want are mean, standard deviation, range, min, max. Right? So we can highlight this, click play, right, this little play button up here, and it'll run our data. So keep in mind this is a dollar value, so just know that. So we have a range of 6,000 minimum, 178,400 maximum, a mean of roughly $77,027 on average, with a standard deviation of 36,426. Really large standard deviation. All right? So we have those descriptives. And what we're doing is we're comparing this mean to the Michigan State mean of $106,000. So let's do that now. So here, again, we're going to run a one sample t-test. Again, we're going to go to Analyze. We want to go to Compare Means. And all of the t-tests are in Compare Means. Right? So we have our one sample test, our paired samples test, and our independent samples test. And so we'll go over each of these. One sample test here. Want to run that. So what we're going to do is we're going to put our 2015 faculty salary for UW-Bothell in the test variable. And then we want to set our test value. Now this is the value that we're testing against, right? because, so this is our population statistic as a textbook would typically talk about it. And so for MSU, for Michigan State, remember it was $106,000. So we want to make sure we have that right, $106,000. That's our test value. So we're testing the average faculty salary at UW-Bothell versus the average faculty salary at Michigan State University. And we want our options here. Confidence interval percentage is 95%. This is our alpha level, right? So this is our critical region. So we could set this at 99%, 95%. The typical is 95%. And then we're going to exclude cases analysis by analysis if we're running multiple t-tests. So we'll just keep this clicked here. And then again, we click paste because that will paste our t-test command into our syntax. And so we have t-test, right? And so our t-test value is 106,000. And so the nice thing about this, right, is you can use this and you can run multiple commands simply by copying and pasting. And we could do the 2015 data, or excuse me, 2017 data as well, right, and compare that to 106. We can change our confidence intervals, so it's nice because we can manually change some of the criteria here. So we have our values here. We'll highlight. We'll press play, and here's our output, right? And so what we've got here is we have several pieces of information that we need to know. All right, so here's our descriptive statistics. It's similar, exactly the same as what we have here, right? So in this descriptives box, we have the one sample statistic, so it's the same thing. A sample size of 65, a mean of $77,027, standard deviation, and the standard error mean. We don't need to pay much attention to this. And so what we're doing is we're going to compare our this statistic to this value of $106,000. So this is our output. This is what's telling us whether or not we are statistically different than Michigan State, right? And so our t-value is negative 6.143. So this is a fairly large t-value with our degrees of freedom of 64. These are important things to know. So this t-value here, this is our test statistic, right? So I'll highlight this. So that is our test statistic. We need to know that, right? This significance two-tailed tells us whether or not, and so again, this is a two-tailed value, which might be slightly different, which would be slightly different if we have a one-tailed value. But this is telling us whether or not our model is statistically significantly different. And so what this is doing is saying, so we set our confidence interval at 95%, right? Or again, our alpha at 0.05. If this is less than 0.05, what this is telling us is that our test statistic falls way outside of the tail. So our t-value is beyond that critical region that we set at 95%, right? This is beyond that 95%. So the potential of this happening by chance, or this result happening by chance, is extremely low, right? So we can almost think of this as a percentile. It tells us the mean difference between the two values, between this value and this value, or excuse me, this mean up here. So it's mean minus mean for the two values, and then our confidence intervals, and we talked about this earlier in the class. So that's our one sample test, right? So now I know that there is a statistically significant difference between our two values. So what I would do is I would interpret the results, right? And I would say something like a one sample t test was to investigate whether there was a difference in salary between MSU faculty and UW faculty. I found that, and just a side note, you're going to want to use this basic sort of formula, if formula is the right word here, but this basic format to write all of your results from here moving forward. So we're talking about t-tests, we're talking about ANOVAs, all of those inferential statistics are going to be using this basic format, right? So I found that on average, right, because we're looking at a mean, MSU faculty make, let's say, have a greater salary. So significantly greater matters, right? And when I say significantly greater, what I'm referring to when I go back is that, when I go back to the output, what I'm referring to is this t statistic, right? So the significance of this test statistic. So there is a significant difference, right? So let's head back to this. I found that on average MSU faculty have a significantly greater salary than UW-Bothell faculty in 2015, and here's where we want to put our test information. So we will say something like T with the degrees of freedom. So our degrees of freedom is 64. T64 equals, and then we're going to look at this test statistic here. So we're going to add this in. So I'll just copy that. Equals negative 6.43 with a p-value of less than 0.05. Yep, and that's what we have, right? So we have our p-value, we have our test statistic, and those are the two main components of your results. So you want to add those in so the reader can understand, or at least have an idea of the statistic that you ran, right? So that's a general piece of the one sample test. All right. So we do have our results here. Interpretation of those results are important. So what I'm going to do now is I'm going to move on to the paired sample case. And I'm not going to, for time, I'm not going to write all of this out, but I'm going to run through the analysis fairly quickly. And so the one sample, or the paired sample case, remember we're comparing something like time 1 versus time 2, right? So I'm interested in the question, does a 2% raise every year equate to a statistically significant raise, right? And in this case, statistically significant means that it's greater than 0, right? It's significantly greater than 0, given our error, given our confidence intervals, right? So what I want to do here is I want to go to my Analyze. Again, compare means, and then we want our paired samples t-test. So we'll run the analysis again. We'll compare 2015 faculty salary to 2017 faculty salary. So again, I might state a research question such as, is there a significant difference between faculty salary in 2015 versus faculty salary in 2017? Options here, just keep it set at 95. That's sort of our go-to for most things. And I'm going to paste. You can click OK and it'll run the analysis, but I'm going to press paste because I like to keep my syntax. I'll go back to my syntax here, and we have a bunch of room, but there we go. So this is our, and I will call this the paired sample test, and we want to highlight this and click run. And again, let's go through this. So we have our paired sample statistics. So we have our means of faculty salary in 15 versus 17. sample size, standard deviation, so on and so forth. Then we have the correlations between the two, so it's a direct correlation, which is great. It is what it is, and so let's run through here. So our mean difference is roughly $3,100. The mean standard deviation between the two is $1,400. Standard error of the mean, and then here's our confidence intervals of the mean difference. So our lower and upper confidence intervals of the mean difference, and here's our test statistic, right? So this will be compared to our critical region, our degrees of freedom, and then our significance level. So again, if this is less than 0.05, we will be rejecting the null hypothesis. Or in other words, if it's less than 0.05, we're accepting the research hypothesis, right? So in this case, what this is telling us is that there is a significant difference in faculty salary between 2015 and 2017. So faculty had a significant raise during that time. Right? And then finally, let's run an independent samples test. So I'm going to copy this. Samples test. I'm going to take this off because I'll run this manually. So now let's take a look at the independent samples test. So let's do compare means, independent sample t-test. And let's say in this case I'm interested in whether or not faculty with chili peppers, let's say have higher ratings, right? Higher ratings than faculty without chili peppers, right? So maybe my hypothesis here is that if students perceive faculty as more attractive, maybe they'll give them higher ratings. That's kind of the idea here. So we're going to do, does this professor have a chili pepper? Right? And so what we're going to do is we're going to move this into the grouping variable, and we're going to define our groups. So group 1 is chili pepper, group 2 is no chili pepper. Right? And what we want to do is let's take a look at overall quality. So let's see if students rate professors who are more attractive as having a better quality. Again, 95% confidence interval, press continue, press paste, right? And we have this, we can bring this up here. And as we can see in our syntax, we have our grouping variable, which is Q9in. This is our hotness variable with our two groups, 1 and 2. Our missing is going to be analysis, and this is our outcome variable, or a dependent variable, and our 95% confidence. So let's go ahead and run this. So, wow, that's actually significant. That's interesting. So, we have 22 faculty versus 49, and what we see here is that we have faculty who are rated as more attractive have a higher general rating compared to those who don't on average. Now the question is that a statistically significant average? Right. So let's run through this. Levine's test for equal variances. Just to keep this simple, just stay on the top row here. So just always assume equal variances, right? And if you were to run this statistic in Excel, Excel always assumes equal variances. So just make that assumption, right? So now let's go through each of these. So our Levine's test for equality of variances, we can ignore this. We don't want to think about that, because that tells us whether we go to this column, or excuse me, row versus this row. Again, we're only going to use the top row, so let's just not think about that right now. Okay, well, this is tripping, so I'm going to close that out. So let's reopen it. So let's look at our test statistics, or our statistics. So we have our test statistic here, which is 4.270. Our degrees of freedom, and then our significance, right? So again, this is less than 0.05, so we are going to reject the null hypothesis. So what this is telling us is when we look at the means, we know that faculty who have chili peppers are rated as higher. than faculty who are not. And this tells us that they're rated statistically significantly higher, right? And so, so we can come to that conclusion and we can write our results. And just because we've done this for all variables that have been significant, let's take a look at a variable that's not significant. So I ran this before, and I want to do this again. So let's take a look at the independent samples test. And so let's keep this grouping, hot, chili pepper versus not chili pepper, and then let's take a look at salary. So perhaps, and we know this from the social sciences, that people who are deemed as more attractive, meaning taller, in good physical shape, for example, tend to make more money. This is just what we find in the social sciences. So let's see if that's true for our faculty here at University of Washington, Bothell. So again, I'm going to press paste. You can see our test here. Bam, there we go. So everything is the same with the exception of this Q10, right? So this is our outcome variable, or our dependent variable, compared to what was our rating before. So let's run this. Right, so fortunately, what we see is that actually on average, faculty who are rated as, or I should say, do not have a chili pepper, tend to have, on average, more income than faculty who have a chili pepper. Perhaps we have a sphericity issue here, meaning that some third variable is related to both of these, and I would think maybe perhaps age. Perhaps students just give chili peppers to younger faculty, right, who tend to make less money than older faculty because they're more senior, right? That's a fairly typical response, or typical answer to that. So let's take a look at our test statistic here, right? So we have negative 0.502. So very low T statistic. We have our degrees of freedom here. And here's our significance, right? And this is greater than 0.05. Because this is greater than 0.05, we reject the research hypothesis and accept the null hypothesis in this case. And so in this case, the null hypothesis would be that there's no salary difference between faculty with chili peppers and faculty without chili peppers. Right? So that's what this would look like when you have a statistic that is not significantly different. This is going to be greater than 0.05. Okay, so that's what I have today. So hopefully this was informative and helpful. So this was how to run a one sample test, a paired sample test, and an independent sample t-test. I hope you enjoyed. Thank you very much.